welcome, folks. Today we have a very fun activity. This is called a cuatro, and it's called cuatro because it has 4 strings. And cuatro is 4 in Spanish. We don't have too much creativity naming our instruments. And we're going to use this at the very end of the class to discuss Fourier transforms. So that's why I have brought it with me. Okay, I think you're safe there. So, today is the 5th iteration of our Coming Up to Speed course. As usual, a reminder of you to be nice to yourself and to each other. The slide that has the information about the resources with all the links, the drive where I'm putting everything, the GitHub repository where we have the coding, including the one that we're going to use today for the Fourier transform, and the forum and the YouTube channel. This is a summary of the lecture from last time. Maybe I should have asked, Gabi, are you okay?
Yeah.
Spotlighting the summary? Okay. I keep forgetting to ask people. Anyways, last class, we talked about normal modes, and I wanted to share the idea that beyond the traditional thought that most people have when they think of normal modes as these vibrating things, this encompasses a much bigger spectrum of ideas that are states that make a system, an equation, an operator, a matrix, a Hamiltonian, whatever makes it trivial. And we were talking about the normal modes in particular with respect to the rope, and we discussed how, if I want to model this system, modeling this mechanical system means finding a function that describes the position of the rope at each location x and at each time t. That's a very hard problem to solve. But if you decided to break it down into the normal modes, the eigenstates of the rope equation, which we haven't defined yet, you will have a much easier time modeling it. Because now, instead of trying to understand what happens to each individual piece of the rope, what you need to do is decompose your initial condition of the rope as a linear superposition of the normal modes up to a certain value that you decide after that is not necessary. And then you just need to find these coefficients and you're done. And the way that you find these coefficients, if you remember, has to do with projections, which has this idea of using a lantern to cast the shadow of one function on top of another. And mathematically, that means doing the integral between the two functions. Whenever we work with complex value functions, we're going to have a complex conjugate in f here, but for now we don't have to worry. And the reason why it's an integral is because if you think that functions are vectors, which you can convince yourself that they're obviously vectors in an infinite dimensional space, the integral is just a generalization of the dot product between vectors. Make sense? Any questions with respect to that part of last class? Any comments? You go back home and couldn't stop thinking about the normal modes and how important they are for every piece of math and engineering that you do? Yeah, that's what I did that night as well. The second part, or the final part of the class, we started talking about linear algebra in terms of matrices as operators that act on vectors. And the analogy that I was driving is that you can think of these operators as cooking instructions. And the vectors are ingredients that you have in your kitchen. And based on that analogy, some of the instructions could be cut or freeze, and some of the vectors can be chocolate or onion or water. And depending on how you apply the matrices to the vectors, you will get new vectors, new ingredients, or new states. And we talk a bit about how these things don't commute. Cutting water and then freezing it doesn't give you the same as freezing it and then cutting it. Any questions or comments with respect to that? Have any professor ever told you that linear algebra is like cooking? Well, I'm glad that we are able to see it this week. Okay, these are reminders of the playgrounds, playground 1 and 2 and 3 and 4, which was kind of a mix between the new concepts on the matrices and the projections from the previous part. Anybody had any chance of playing with any of these things? Daniel, you were going to say.
Oh, I did not get to do 3 and 4. So okay. I went to look at what it was and it wasn't posted. So
I'm sorry. Then I do need to post it in the forum in the playgrounds, but I think I updated some of the drives yesterday. Oh. But absolutely no hurries. I'm just happily waiting until we have some discussions about these things because I think they're going to help you get better understandings. Any other comments or questions with respect to this? We're actually going to do basically problem 2 in class today. Okay? So let's think using one of my favorite matrices because it's very easy to understand. This friend that is here. We're going to label this as the matrix M. It's a two-dimensional matrix. That means that it acts on a two-dimensional vector space that is made of arrows. I'm going to use, because we're going to talk about this later and it's important, I'm going to use the basis that is x hat and y hat. These are my basis vectors, at least at the beginning. And this matrix in that basis looks like this 2, 1, 1, 2. Make sense so far? So if I were to ask you, friends, what does it mean when I say the vector 1, 2? This is equal to what? In terms of my basis vectors. Fantastic. Thank you, Gabby. 1 x hat plus 2 y hat. Make sense? If later we have a different basis, well, we're going to have to be careful what those numbers mean. Yep, everybody follow. All right. So let's try to get an intuition. That is a playground that I gave you last time. I want to have an intuition on what this matrix does to the entire plane. Let's start asking ourselves, what happens if I do M acting on x hat? What is this equal to? How can I compute this operation? So, how do I perform this operation? Any idea?
Take matrix M and then convert x hat into a vector.
So, I do the matrix 1, sorry, 2, 1, 1, 2, and this applied to the vector?
1, 0.
Excellent, thank you. And this is equal to how much? So I imagine you have multiplied matrices before, but just in case, you grab this and you multiply by this, and that is going to give you 2 times 1 plus 1 times 0, that is 2. And then this multiplying this is what gives you this entry. Is everybody okay in how to multiply matrices, or that is something that you would like me to go over? Matrices times vectors. So how much is the second entry?
1.
Perfect. Yep. Yep. Everybody happy? This is the moment where you say, I'm not, please stop. Okay. Very good. So, oh, by the way, Hannah, I think you're the only person online. So anytime that you need to, just unmute yourself.
Okay.
And I realize that, okay, yeah, well, we can do it. Okay, so, so this is a vector 2, 1, which means 2 in x plus 1 in y. I want to draw that vector. So that means I have to move 2 units in x, that is here, and 1 unit in y. So this blue friend is the action of M acting on x hat. So it kind of stretches it a bit, and then rotates it a bit up. Yep, everybody sees that? What would be the action of M acting on y hat? Anybody? Can you tell me directly the vector that I obtain in here? 1, 2, right? Because you just multiply the matrix M by the vector 0, 1. And that is basically going to give you this column, right? No, this column. Yes. Yes, this column. All right. So that vector is 1 in x, 2 in y. So like here. So you see that the action of this matrix on my vector y is basically stretches up a bit and rotates it a bit to the right. Well, this one, stretch it up a bit and rotate it a bit to the right in here. Everybody sees that? What do you think, based on your intuition, what you're seeing in here, what do you think is going to happen to the vector, let's say, let's consider the vector -1, 2. So that vector will be here. This is a vector v. V is equal to -1, 2. I promise this is the last one that we're going to do. How much is m applied to v? This is 2, 1, 1, 2 applied to -1, 2. And this is equal to 2 times -1 is -2, plus 2 is 0. I hope that you check my math. Otherwise, this will be recorded for eternity and it will be wrong. And then this is 1 times -1 is -1, plus 4 is 3. Yeah? So 0, 3. So this vector that was 1, 2 gets stretched a bit, put it in red, and gets mapped all the way in here. So if you had to make a guess of what this matrix is doing to the plane, do you have any idea?
Stretches it and rotates a bit.
Stretches and rotates a bit, but it's a bit weird because you see that the vectors that were on the left of this diagonal were rotated clockwise, but the vector x that is outside of that was rotated counterclockwise. So it's not just a stretch and a rotation, it has to be something else. So the question that we're trying to answer here today, is there any way in where I can understand, I can have a geometrical intuition of what this matrix is doing without having to continue computing what it's doing to vectors? Basically, is there a set of vectors? And this is such an important question that I'm going to write it. Is there a set of vectors that make the action of M look trivial? You see that it's a very similar question to what we were trying to answer last class with the rope. I cannot solve what will happen to any arbitrary configuration in the rope. There is a set of conditions, a set of vectors, functions, whose evolution in time is trivial. Sounds that, given that that is the title of today's lecture, probably that's what we're going. So the idea of an eigenvector of a matrix is exactly this. And what will be trivial in the sense of matrices means that you grab the matrix M and you multiply it by a vector V, and that ends up being exactly the same as multiplying that vector V by a number, stretching. Why? Because then I think that's the simplest linear operation that you can make. See that all the operations that we did, they kind of stretch the vector a bit, but they rotate it, and they don't rotate it always by the same angle, so it's kind of a mess. So I'm trying to look, will they be a vector where the matrix just stretches it and doesn't do anything else? Make sense? From this picture, could you guess what is at least one of those directions? See that X was turned this way and Y was turned this way.
1, 1.
It seems that if I were to consider the direction 1, 1, that is its diagonal, well, shouldn't turn either left or right. It's an heuristic, we'll have to check it, but that's probably one of the directions that we're thinking. And if you had computed everything else, you will realize that the vectors that were around here were actually being rotated to the other side. So I will imagine that there is a complementary line that is going to be the line -1, 1, that also is not going to get rotated. And those are the two vectors that we're after. Now, how do we find that? You could, in principle, write this equation the way that I have written it, in where you will have your matrix M. This is 1, 1, 2, 1, 1, 2, acting on a vector V. I'm going to put it Vx, Vy. Those are two incognitas that I do not know what they are. This is equal to a number lambda Vx, Vy. And then this is an equation in vector space. Basically, it's two equations put together in a trench code. But I have three incognitas. I have Vx, Vy, and lambda. And it's kind of annoying because actually, if you find a solution to this equation as a vector, 3 times that still will be a vector that is an eigenvector, 10 times as well. So the system is a bit funky. We need to find a way of simplifying this. And what we're going to try first is, can we find lambda? Can we obtain first the number, the eigen value, the eigenfrequencies of this matrix operator M? So I'm going to start writing math. Everybody's clear of what we're trying to do. Does it make intuitive sense? Yep. All right. So how do we do that? Well, as humanity, we have been thinking about this problem for a long while. And we have found out that the easiest way to think of this is, you say, you're trying to solve matrix M times vector V is equal to, I'm going to write it as the identity matrix times lambda. Why? Because I am going to start playing with matrices, and having lambda times vector is correct, but it makes the calculations a bit more complicated. We need to think what we're carrying around. So I haven't done anything. I have just said there is a matrix in here that is the identity matrix, 1, 1, 0, 0. So if you multiply the identity matrix by lambda, basically you get a matrix that is lambda, lambda, 0, 0. And that just stretches the vector in that direction. But if these two things are equal, that means that I can subtract and say that this is equal to 0. Look what I'm going to do now. I'm going to say, that means that the matrix M minus lambda times the identity, all of this matrix, when I apply it to the vector V, this gives me 0. This tells you this is a very naughty matrix. Why? Because this matrix as a whole kills vectors. This is a matrix that grabs a poor innocent vector that was lying around minding some business, and it multiplies it by 0. That has a name. It's called a singular matrix. And they're super duper important for many reasons, and you will see them later throughout the course. But that's the key. The key is to realize I am trying to find a lambda such that when I plug it in this equation, the matrix that I obtain is singular. It kills a vector. By the way, the vector that it kills, it will be the vector that we're after. That will be the eigenvector. How do I know if a matrix is singular? Bunch of math that we're not going to prove, but basically you can write the operation that is called the determinant of this thing, and a matrix is singular if and only if the determinant is 0. And the way to think it intuitively, the determinant of a matrix basically is telling you, in a matrix, in a 2 by 2, 2 times 2 case, which is a plane, if you were to grab a square and you apply the matrix to the edges of that square, it transforms in a way how much the area of the new square that you got gets multiplied by. And if one of those vectors gets multiplied by 0, you're basically mapping a square into a single line. The area went from something to 0. So that determinant is going to tell you, you can imagine this as a beeping, a Geiger counter that is like, it's going to become 0 whenever you're near in the presence of a singular matrix. Yep. All right, let's write it. For the 2 by 2 case, the determinant of this matrix is going to be determinant of 2, 1, 1, 2 minus lambda 0, 0, lambda. And this is equal to the determinant of the full matrix 2 minus lambda 1, 1, 2 minus lambda. Anybody remembers how to algorithmically calculate determinants?
Essentially, down the 2 minus lambda diagonal.
So I grab these two and I multiply them, and then I subtract the multiplication of these two. I only remember by memory how to calculate the determinant of a 2 by 2 matrix. The 3 by 3 is a bit annoying, but you still can. Beyond that, don't even try to remember. Computers know how to do this, and you can just trust the computer. So how much is this? It's going to be 2 minus lambda times 2 minus lambda. So that is 2 minus lambda squared minus 1, and this is equal to 0. Now, this is an equation in lambda only. If you plug in any lambda that you like, let's say you plug lambda equals 10, 2 minus 10, that is 8. 8 squared is 64. 64 minus 1 is 63, and that is not 0. So most values of lambda that you can think of course, will not solve this equation. It's a specific set of values that will give you a solution to this. So now we have to solve it. So this is equal to 2 minus lambda square is equal to 1. I take square root, and I need to remind myself to take the plus minus. So this is 2 minus lambda is equal to plus minus 1, because the square could have collapsed that information. Then 2 minus plus 1 is equal to lambda. And from here, I get that lambda is either 3 or 1. These are the two possible solutions that I get to this equation. Yep. Are we done? Do I now have an entire intuition on what the matrix is doing to the plane? Or what am I missing? I have the eigenvalues, but I know that they're going to be stretched by 3 and 1 respectively, but who are the eigenvectors? How do I find that?
Plug in the values of lambda
in where?
To the, it's where we started.
Very well. I have an equation that looks like this. I'm going to go down. I suggest that if you don't feel super comfortable with everything that I have done today on this, you try it out by yourself. It's the type of things that once you have done it enough times and you get the intuition, it's obvious. It makes sense, everything that you're doing. But I have seen a lot of people, myself included, whenever you're not really understanding why you're doing this, that you get confused in steps. We have the eigenvalue. Now I need the eigenvector. So I'm going to grab this equation and I'm going to say lambda. No. That was not lambda. That was a number 3. And now I'm going to solve this. And this equation tells me the matrix 2, 1, 1, 2 applied to the vector Vx, Vy should be equal to 3 times the vector Vx, Vy. And now we solve. So what do I get? I'm going to write it in black. 2Vx, I'm going to multiply this times this. 2Vx plus Vy is equal to 3 times Vx. And I get 1Vx plus 2Vy is equal to 3 times Vy. For those of you that have had experience with system of equations, you will realize that these two equations are redundant. I can actually just focus on one. And what I get from the equation on the top is that Vy is equal to, I'm going to pass the 2 subtracting to the right, Vy is equal to Vx. And the second equation will tell you the same. Now, if I want to obtain an eigenvector that has norm 1, I just need the two values to add up to 1 whenever you square them. So can you tell me what is my normalized eigenvector? I'm going to call this friend phi 1, actually, because we're going to use that notation. 1 over square root of 2, 1, 1. That is my first eigenvector, which is exactly what we were saying. Remember, when we were looking in here, this is the vector, this is the vector 1, 1 with the square root of 2. That now we understand this thing just gets stretched by 3. And that's why everything that was around, it was kind of like getting stretched and rotated towards this friend. Make sense? What about the second eigenvector? What do I do? Same thing, but we won. I grab and I duplicate this thing in here. Put a 1. And I get 2Vx plus Vy should be equal to Vx. And the second equation is redundant. So I subtract to the left and pass this one to the right, and I get Vx is equal to minus Vy, which comes back to the intuition that we were having before, that the second vector phi 2 is equal to 1 over the square root of 2, 1, say minus 1, 1. So the two eigenvectors of this matrix, I'm going to draw this thing again, are, let's put them, I'm going to put you in red, I'm going to put you in blue. It's the vector 1 over square root of 2 minus 1, 1, and the vector 1 over square root of 2, 1, comma 1. And the action of the matrix M, when it acts on this vector, it multiplies it by 3. And when it acts on these vectors, it multiplies it by 1. So now you have an intuitive picture of what is happening. Everything along this direction gets stretched by 3, and everything along this direction gets left unchanged. Any other vector that is flying around, if you think of it and how it will look as a linear superposition of these two eigenvectors, you will be able to understand what happens to it. Make sense? Please.
The eigenvector could also be 1, negative 1, or?
Of course. We think of vectors as arrows, and we had this exact discussion last class. Technically speaking, math-wise, more than an arrow is a line. Is this entire line is the eigenline of M. Any vector that lies on that line is an eigenvector. The same with the other one. It's just that as physicists, it's a bit more awkward to think of an entire line, so we usually think in terms of that arrow. But if you multiply by minus, that's fine. If you multiply by 10, that's fine. It will still be an eigenvector. So very good question. Thank you. Any other questions or thoughts? So far, doesn't seem very useful. Seems even a bit boring. But this is at the heart of a bunch of stuff that you're going to use in the rest of your class and in research, because the main idea in here is, now that I come and I tell you, I have a new vector. Let's say the vector that we were having before, what was it? I think it's a 1, 2. And I want to understand what happens to this friend when I apply the matrix. If you decompose this vector, let's actually do that exercise. If you decompose V, which is 1, 2, and I'm going to put it in here, remember, in the x hat, y hat basis, if somehow I was able to write this as a number A times, actually, let me not mix the colors. A number A times phi 1 plus a number B times phi 2, then see what will happen. Whenever I grab the matrix M, apply to the vector V, this is going to be equal to 3 times A times phi 1 plus 1 times B times phi 2. Because the matrix is going to act on the addition of these two friends, and phi 1 is just going to be stretched by 3, and phi 2 is just going to be stretched by nothing, by 1. Makes sense? How do I find these coefficients?
You can plug in phi 1 and phi 2.
What do you mean?
The vectors.
So for example, these, I think I see what you mean. So to write A times the vector 1 over square root of 2, 1 over square root of 2, plus B minus 1 over square root of 2, 1 over square root of 2. And this should be equal to 1, 2. And then I have two equations with two unknowns, and I can solve. Perfect, that works. That's one way of getting that. I'm going to suggest a different one that will help for any such situations. Can you find a way of writing x hat as a linear superposition? I'm going to write it in this way: ax phi 1 plus bx phi 2, and write phi y hat as ay phi 1 plus by phi 2. Because if you find these numbers, see that what you can do, you can say, well, this vector here that was equal to 1, 2, this is equal to 1 x hat plus 2 y hat. So once you have this mapping, what you can do is go and substitute x hat and y hat in their phi1 and phi2 expansion, and that automatically gives you everything that there is to know. Make sense? Your method works completely well. It's just that I will have to apply it every time that I want to do this. I think with this, we do it only once and we're happy. Okay? So help me. How do I write x hat as a linear superposition of these two vectors? And I'm going to remind you, phi1 is equal to 1 over square root of 2, 1, 1. Phi2 is equal to 1 over square root of 2 minus 1, 1. How do I do this? You could do dot product. That is true. I think you can guess it in this case. You can set the system of equations as Gabby said and solve it. I want you to guess it. What is a guess? What are these two numbers? What are the coefficients that I need to multiply phi1 and phi2 to obtain the vector 1, 0? So what happens if, for example, you say ax is plus 1 and bx is plus 1? What would you get if you add these two vectors? If you add them, you get 1 over square root of 2. These two ones cancel, so 0, and these two one add up together, so you get a 2. That looks like y hat with some weird, so that doesn't work. That will work for the second case, but for this one doesn't. What can you do if you don't add them? I need to convince this one to not interfere with this one, but rather to help each other. What do I do?
Negative.
Negative. So if I put a negative, I get 1 over square root of 2, 2, 0. But I wanted to get 1, 0. So if I put these two outside, and if I were to multiply this whole thing by square root of 2 over 2, then I'm done, because it will cancel that square root of 2 over 2. So that is how you guess it. Basically, this friend is square root of 2 over 2 with a minus, and this friend is square root of 2 over 2 with a plus. And what do you think I need for the y case? The same thing, but positive. For those of you who have seen quantum mechanics, you will realize that these numbers look very similar to whenever you have the plus, 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 minus, minus, plus, minus, minus, and you're playing with them and you're trying to find linear combinations of them that rotate your bases. Hannah, you following me so far?
Uh-huh.
Excellent. Very good. Okay. So then, if this is what I have, I leave it for you as an exercise. I recommend that you try it. Try to plug this back in this expression for v, and see what happens whenever you say x hat, you replace this x hat by square root of 2 over 2 with a minus phi 1 plus square root of 2 over 2 phi 2. And the equivalent for y hat. And that will give you that transformation for expressing the vector b as a linear superposition of the phi's. I'm about to start talking about changes of bases, and then I'm going to give you the activity for today. Any questions on what I have done so far? You're following? We're all a bit sleepy. I'm also sleepy today. I think it might be the weather. The plants didn't provide enough oxygen. Okay, so that is the idea. What I want to propose that you think is, how will the matrix M look if we were to write it in the basis of eigenvectors? The matrix M, remember that when we write anything that looks like this, and I say 2, 1, 1, 2, I'm doing this between friends, because I know that you know what I mean, but in principle, I should put a tiny parenthesis in here and say, this is in the x hat, y hat basis. And I should put it also in here. This is the representation in the x hat, y hat basis. Because if I have chosen different vectors, the matrix will look different. In particular, do you have any intuition on how this matrix M would look like if I were to grab it in the basis of its eigenvectors? What do you think these numbers will be?
Will just be the identity.
The identity. Almost, Let's unpack that. So you're saying I should put a 1, 0, 0, 1. Let's think of the implication of what you suggested. That means that M in these bases acting on the vector phi 1. By the way, how do I write phi 1 in the phi 1 and phi 2 bases?
1, 0.
Oh, I'm so happy. Yes. So this means, let's test your hypothesis. This means the matrix that will be 1, 0, 0, 1 acting on the vector 1, 0, this is going to be equal to 1, 0, which is equal to 1 times phi 1. Are we happy that the action of M on phi 1 is just to multiply it by 1? Are you sure?
Do we need the eigenvalues?
I don't know. You need to tell me. But when we talk about this friend, remember the graphical intuition was, oh, this is going to be stretched by 3. So your matrix is telling me this vector will remain in the same direction, but it will remain with stretching 1, but that's not true. You see it. So what do we do? What can I change?
Would it be 3, 0?
Oh, that's fantastic. If you put a 3 in here, then you're done. At least for phi 1, because then this is a 3, and this is a 3, and this is a 3. Yep. What about the second one? Well, the second one turns out to be exactly a 1, because that eigenvalue was 1. So this is how the matrix in the basis, in its basis of its eigenstates looks like, which makes sense. That's what we have been saying so far. We have been saying, oh, this thing should look trivial if you write it in terms of its own eigenstates. Yep. Beyond having that intuition, I want you to work on it and try to convince yourself on that. So how does this change of basis work? The analogy that I have for you is I want you to think, I told you that matrices were like cooking instructions. I want you to think in terms of language and translators. Okay. I want you to think of the matrix M more than just a particular instruction like cut an onion. I want you to think of this as a chef. And what happens on this chef, it will receive ingredients and it will receive instructions in a specific language, and it will give instruction back on that same language once the object is transformed. So for example, if this chef speaks Spanish, the incoming instruction better be in Spanish, and whatever the chef processes and outputs back is also going to be in Spanish. But suppose now that I need to put this chef, famous chef, fantastic, it's me. I speak Spanish and I'm an incredible chef, world renowned. They take me to France and they want me to cook in one of these very fancy restaurants. I don't speak French and I don't understand anything of anybody that anybody's saying around, and I need to interact with them. But I'm so good that the restaurant is willing to pay as much money as they need so that I can work in there. What would you do if you were the restaurant? And I refuse to learn French. That's too hard for me. What do? We hire, with technology, you can do that, but let's make it expensive. We're going to hire 2 people, a translator A and a translator B. The objective of this translator is an instruction is going to come here in French. This translator is going to output that same thing, but in Spanish. I am going to process it. I'm going to say it in Spanish. And then the final translator has to revert it to French. Does that make sense? That's the idea here. So what we're trying to do is to say, well, I know, now coming back to matrices, I know the matrix M in the X hat, Y hat basis looks like this. I want to write this matrix in the phi 1, phi 2 basis. This is going to look like something. I have no idea what this is. But one way of solving this is I'm going to put my translator. This is going to take a lot of space. So basically, this will look like my matrix in the X hat, Y hat basis. In here, I need a translator. Translates if I want to write this matrix in these bases, that means that the input that is coming from the right is going to be a vector in phi1, phi2 language. Yeah. And then I need to multiply, because of the order on how matrix multiplication works, I need to multiply by another translator that outputs this in the bases phi1, phi2. So this translator translates this vector into the x hat, y hat, and this one translates it into from x hat, y hat into the basis of phi1, phi2. So how do you do that? Well, I need, remember that if you have a vector b that is written as a times phi1 plus b times phi2, what you need to do to be able to make this change of bases is to find how to map phi1 and phi2 into the x hat, y hat. Once you have that, you're going to be able to translate vectors that are in the phi1, phi2 bases into vectors that are in the x and y bases. And the easiest way to do that is to say, well, what if you start with the vector that is just phi1? This is a vector 1, 0. So how can I write this as a linear combination of x hat and y hat? Do you remember? It has been a while since we look at that. So this has to be something x hat plus something y hat. What were these numbers? Do you remember them?
Oh, they're 1, 1.
Yep. So square root of 2 over 2, square root of 2 over 2. Yep. How about phi 2? This is a vector 0, 1 in the basis of phi 2. You see, this, be very careful. This is in the basis phi 1, phi 2, phi 1, phi 2. Everything that is on the right is on the basis x hat, y hat. So how much was this? You remember?
Minus 1, 1.
Sorry?
Minus your 2 over 2.
Excellent. So these bases, this matrix that I'm talking about, let's call it matrix change basis and matrix change basis to the -1. This MC should be a matrix that if I hit it with the vector 1, 0, which is in the phi1, phi2 basis, what should the vector that I obtain look like? I believe in you. This is phi1, phi2, and this is x, y. Yeah?
1 over root 2.
Excellent. Everybody's seeing that. Let me put it in red. Square root of 2 over 2, square root of 2 over 2. That's what this equation is saying, because then this is equal to square root of 2 over 2, square root of 2 over 2, and this is equal to minus square root of 2 over 2. You following me, friends? You sure? So this is what this matrix should look like, and I'm going to show you how I figured these things out. So this matrix is a matrix that has 4 numbers that you do not know yet, but when you multiply it by the vector 1, 0, you get square root of 2 over 2, square root of 2 over 2. Can you tell me anything about these numbers?
For the right column, it doesn't seem to matter what's in it.
The right column doesn't matter for what is happening in here, because whenever I grab this friend and I multiply in here, the right column doesn't matter, and when I multiply in here, the right column doesn't matter. What can you tell me about then the left column? What are their values? Fantastic. What about the second column then? How can I figure out what is that? What do I do? We do the exact same thing, but instead of this, we put 0, 1. And what is the decomposition of phi 2 in terms of the x hats? I just need to put a minus here. So what is that column?
Minus.
Fantastic. Yep. Okay. So here is your in-class activity. I'm going to put the PowerPoint in a second. I want you, so this was MC. I'm going to put in parentheses. translates phi1, phi2 bases onto x hat, y hat bases. You need to find the complementary one, mc to the minus 1, which does the opposite. Grabs vectors that are written in the x, y system, and it translates them to vectors that are written in the phi1, phi2 system. And after that, you're going to perform this multiplication. You're going to multiply mc to the minus 1 times m. This is m written in the xy hat basis times mc. And I'm going to pray very, very, very hard that what you get looks like this. And this is what a change of basis matrix means. It's something that translates so that you can use the operator that you had in its original form. And if everything that we did worked well, you should recover something that looks diagonal. Make sense? Okay. Let me stop sharing here. Okay, so it is 2:20. I'll give you 4 minutes. You have until 2:24. Give it a try. Let's see what you get. And after that, we have a 4-minute break. You can team up if you want. You can do the calculations by yourself as well. Okay. So it's a very short time, but I didn't calculate well the time for today, so, and I really want to be able to play with the Quattro. Anybody got anything?
I got 3001 for M.
So you were able to calculate the change of bases, multiply them, and verify that indeed is diagonal?
Yep.
Excellent. What about you, Alex?
Um,
Still in the process?
yeah.
Very good. Recommendation, continue doing that later because it's a good check on your side. Hannah, were you able to
No, I didn't finish.
That's okay, that's okay, that's okay. Take your time later, but Daniel, can you tell me what do you get for the change of bases?
Yeah, for the change of basis, I got 1 over root 2, like from top.
Mm-hmm.
Got 1 over root 2.
I'm going to bet there is a minus here.
Yes.
And then this one.
Yeah.
So I think that's correct. I think I calculated that somewhere, or maybe I calculated only the other one.
Well, I got 1 over root 2.
That's so yes. So 1 over root 2 is the same number as square root of 2 over 2.
Oh, okay.
Yeah, sorry. I prefer to have the roots on top. But yeah, same number. Okay, so finish later your calculations. Do check that when you multiply these two things, you get a diagonal matrix. And that is going to be super important later in many areas, including quantum mechanics, whenever you decide to change to the eigen basis of a Hamiltonian or an eigen basis of one of the operators of your Hamiltonian. So whenever you're talking in terms of spins and coupling and angular momentum, you might have to change bases between the uncoupled bases, the coupled bases, depending on the problem that you have at hand. So feeling comfortable with things is going to be important. I think that's all that I wanted to say about changes of bases. Yes, so now what we're going to do, we're going to take 4 more minutes to stretch our legs, go to the restroom, eat chocolate. It's 2:26. I will see you back at 2:30, and for the last half an hour, we're going to play with Fourier transforms. So the conclusion from our discussions is the eigensystem of a matrix is going to be the set of vectors that make that matrix action look trivial. In the case of linear algebra and actual matrices, it's just multiplying by a number. And you will be very interested in trying to express what the matrix is doing in terms of that basis. To do that, you need to have this idea of these translators that you have to bring them in pairs. You have to bring the translator that changes one basis to the original one. The original matrix is able to act on that vector, and then the matrix that transforms back to the new language that you're trying to use. And to figure out those matrices, what we did was basically try to write the series of equations that tells you how the transformation happens between each element of your basis, the original one and the new one, and that is what allows you to basically write this matrix. There are prescriptions out there in where you can just write this matrix as the columns is going to be the vectors in the new base area. That works. If you want to memorize that, you can definitely do it. I usually always reasoning it through this because it helps me fall asleep better. So what I want to talk about now is Fourier transforms and representations. Here and representations. So if you remember, we discussed last class that if I have a function f that looks like this, and you know we're going to go fully into abstract math, and we're going to just call this for now f. This is my function f. You can think of it, if you discretize your space, that the representation of this function f in a finite grid is equal to a list of numbers. The grid might be very big. I don't know, size n, maybe n is equal to 100 points that you're putting in x between 0 and 1, who knows? But this is basically the value of the function at the first x, the value of the function at the second x, dot, 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 the value of the function at the last x. Is everybody with me? You can think of this as a vector in a very high dimensional space, but what is the basis that you're using? You know, if I write these as numbers, I don't know, 0.08, 0.12, 0.15, etc., these numbers are the coefficients of a basis expansion. I should be able to write this as 0.08 times the first vector of my basis plus 0.12 times the second vector of my basis plus dot, dot, dot. Who are these vectors in this case? Anybody has any idea? I'm going to color them in blue.
Would it be 1 and then a bunch of zeros and then 0, 1?
So if I write them as a list of vectors, I 100% agree with you. This vector will look like, this one will look like. But in this picture, what do they represent? So you're very right. How can I visualize them? It's a non-trivial abstract jump that you have to make.
They're like basis vectors.
Sorry?
They're like basis vectors.
They're basis vectors, but how do they
what
look?
they represent.
And my question is similar to if I told you, in here I have a vector, let's say this vector v, and it's written in terms of the basis x hat and y hat. The answer that I'm after is like, oh, x hat is just this arrow in this direction, and y hat looks like this one. What is the equivalent of that in here? It's a bit tricky, but they're basically rectangles. This is v1, this is v2, this is v3, and so forth. That is what means 1, 0, 0, 0 is a value that is 1 on the first, well, I guess I'm plotting the rectangle times the coefficients, but it's basically a rectangle that is 1 in that area and then zeros everywhere. It's a basis of localized coordinates, such that this function that you're representing here in red, basically, let me write them as this. So if you were to say the first rectangle, I'm doing the same thing again. If they all have value 1, they look like this. And then the coefficients tells you how much you're going to shrink or stretch the first rectangle. In this case, you will shrink it by a lot. You will shrink it by this number. How much you're going to shrink or stretch the second rectangle, and so forth. The details don't matter. What I want you to get is that when you write your function in this coordinate system as these values in this grid, there is an underlying basis, and it's a basis in the x representation that you're using to show your signal or your function. Alternatively, based on what we discussed Wednesday, today's Monday, you could grab your function f that looks like this, and you could decompose it into the normal modes in here. You could say that this is going to be the first normal mode times some coefficient plus the second normal mode times another coefficient, and so forth. So you could write your function f as a set of numbers, but these numbers are not the numbers from before. These numbers will be, in the notation that we were using before, will be a1, a2, dot, 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 an, where these are the Fourier coefficients. These are the coefficients of those waves that you're using to represent these things. Everybody follows me so far? And in principle, and here is a key observation of all of these two are the same object up to a language change. They both represent f, but one of them is using the basis of these squares, these rectangles. The other one is using the basis of the normal modes, but they talk about the same thing. This is equivalent as if I were to bring you Don Quixote de la Mancha, and I give it to you in Spanish, which is how you should read it because that's how it was written, or I give it to you in French. There is the same book. If you read word by word, the words are different. The letters are different. You open a random page at random, and you will see very different things. They're the same book. They transmit the same idea. Makes sense so far for everybody in here? A Fourier transform is grabbing your function that is written in the x or the time domain and is rewriting it in a basis that is a different basis. It's a basis of sines and cosines, but it's the same object. So because we need to find a way of distinguish them, usually the notation that we have, we talk about f of, let's say, x and f tilde of omega. And we talk about the relationship between these two. This is just a change of basis. But how do I change basis? If I give you a function with all the coefficients in the x coordinate, I need to have a map, a way of literally changing the basis, the matrix that you were building. We need to change, we need to find how much is that. And the relationship between these two objects is f of x is equal to, some people divide by square root of pi, 2 pi, those are details, really doesn't matter. The integral of e to the minus I, and I'm going to put, so in here, when I omega x, nope, f of x dx. Now, we haven't talked about complex numbers yet, and that's what we're going to do on Wednesday. So I ask you to be a bit patient with me. I really struggle a lot in thinking in which order I do this, because to talk about Fourier transforms, I do need complex numbers, but I really wanted to connect this when we were talking about change of basis. So for now, just believe me that this e to the minus I omega x is equal to cosine of omega x plus I sine of omega x. And the purpose of this is so that I can decompose my signal in an even function and an odd function. Cosines, all the cosines are even, all the signs are odd. Usually your signal will be a mixture of the two, so that's why we end up transforming it in this way. Does it make sense intuitively so far? Any questions with this? Okay, we're going to play with the cuatro in just a second, but I want to ask you, so what? What is the use of doing this? What will be the use of being able to do a change of basis between an object that, remember, look like this, f of x1, f of x2, dot, 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 to now an object that looks like this? What is the use of this? Why will this be a good thing to be able to do? Sorry? And what can I use that for? If I am engineer, I'm asking you, sell me this thing. I don't want to waste my time learning things that are not useful. Why will this be useful for me?
We know the behavior of different modes.
Okay, can you speak a bit louder?
We know the behavior of different modes.
We know the behavior of different modes. Yeah, that is true. If I was thinking of the problem of the rope, then that is super clear. Suppose that I don't have the problem of the rope. I have something else in where I have a function of x, and suddenly one of your professors or one of your colleagues says, oh, what we need to do is do a Fourier transform. For example, what if you have the differential equation x of t dot dot, let's put a mass in here, this is some sort of a harmonic oscillator, plus a number gamma x dot of t, plus a number k x of t, and this is equal to sine cube of 17t. And I ask you, there is a differential equation, an ordinary second order linear differential equation. Solve it. And you're like, I don't know how to do this. I have a bunch of derivative operators. This dot dot is d at dt squared. This is d at dt. I have a bunch of derivative operators, and I don't know how to deal with them. What if you could do a change of basis to the basis in where the derivative operator looks trivial? What is the eigen states of d at dt? Can you think of a function? I'm going to write this as a big B because I want to draw the idea from the matrices. Can you think of a function or a vector such that d applied to f is just a number times f? Exponentials. That's why we were looking at that differential equation on the very beginning. These are exponentials. So the conclusion from all of these is that exponentials are the eigenfunctions of the derivative operator. That means that this very complicated equation, if I were to rewrite it in the basis of eigenstates of my derivative operator, might look much more simpler. Let's do that. And after that, we play with the cuatro. So that means, and I'm going to say x as a function of time, I can write this as the integral of x hat as a function of omega times e to the minus I omega t dt. I'm going to, let's color this friend like this, so we can track it. So if I write that, then I have my original equation is this. And we're going to solve the rest of this thing in the next class because I do want to take my time with that. But basically, what I want to highlight from here is that my derivative operator, the action in my Fourier basis is just multiplying by a number, which is what we know already. It's going to be just multiplying by I omega twice. And that is going to happen to every term in my differential equation. And after we play with it for a bit, we're going to be able to just transform this problem of a second order linear differential equation into an integral problem. We're going to have to do a couple of integrals to transform from one basis to the other. But if you remember the math dojo, that means that we're moving from an ordinary differential equation to an integral, and that's a win. Does that make sense? Okay, any questions before we go and we play with the quadro? And I'm going to need a volunteer who wants to come here and have your voice recorded for future generations. Sorry? No, you will have to just say something. Come on, Daniel, bring a chair and sit with me. Come and sit. Before I do that, I want to highlight these resources online that helps you visualize Fourier transform in very good ways. The Wikipedia article is particularly nice. It shows you how you have your function. You decompose it into all these sum of sines and cosines. And then depending on the amplitude that you're assigning to each one of these things, when you see that, that is what is going to be the Fourier transform of this signal. It's just a basis change. And 3 Blue 1 Brown, if you have not seen those videos, they are amazing. He has fantastic animations to explain Fourier series. So what we're going to do in here, you're going to come, and I'm going to record you say something. So think of something that you want to say for 5 seconds. You can introduce yourself. You can tell us how the weather is doing. You can tell me what series you're watching recently. So 5 seconds.
Hello, it is way too hot today. Annoyingly hot.
I agree. Excellent. Very good. So what you're seeing in here, thank you, Daniel. You can remain with me. You're going to see what will happen to your voice in a second. What you're seeing here is a time frequency, time signal of Daniel's voice. So we're going to save this, export audio. We're going to call this Daniel. And in my folder in here, I have it somewhere. Is it here? Audio Daniel. Let's hear it. Don't you love when you hear your own voice recorded? Isn't it amazing?
Hello, it is way too hot today. Annoyingly hot.
Okay. So now what we're going to do, I have written with the help of ChatGPT this Python file that you can see in our GitHub repository. And in here, what was the name of the file that we use? I'm going to run it. And here is the time domain of what you said. And here is the frequency spectrum. These are the same function. It's just that I'm reading it in a different basis. And one little thing that we can do, we can grab the spectrum on the right and try to chop it, try to ignore some of the values that we have in there. That's one of the biggest usage of Fourier transforms. You're able to compress signals using much less information because human voice and many sounds have certain repetitions, certain patterns that the Fourier decomposition can actually exploit. So what we're going to do now, we're going to save it using only 50 modes, 500, 5,000, 50,000, and 500,000. Yes. And we're going to see how they compare. Let's see what happens. So what do you think will happen if I, not this one, if I reproduce the same file but with less amount of modes that I involved? What do you think will happen?
What would you saying, like partial words?
Partial words?
So if it's missing certain modes,
And
certain sound.
perfect. Here's the key. If I was missing the rectangles, you're right. You will hear chops in the words. But this basis is a global basis. When you miss a mode, it's going to affect the entire signal. So actually, it sounds kind of wonky. This is with 50 modes. And you remember how crisp your voice was. Let's hear it with 500. Right? 5,000.
Hello, it is way too hot today. Annoyingly hot.
You can distinguish words now. And you see, this is at the heart of a lot of compression algorithms. How do you maximize the information that you keep? That is a useful one.
Hello, it is way too hot today.
Isn't it cool?
Annoyingly hot.
I agree. And then the last one is with all the demos.
Could we see what one of the lower modes ones looked like, Fourier transformed?
Oh, I think that's a fantastic idea. Here you go. Thank you, Hannah. This is with 50 modes. This is with 500 modes. This is with 5,000. And as we saw, this already was sounding very similar with 50,000. And this is with basically the whole thing. And that's how the reconstruction looks like. Now, we're going to record one more. You're going to help me. So whenever I tell you, you're going to click that. So you're going to start the recording. But before we do it, I want you to think with me, what do you think is going to be when I record this D note? How does the signal is going to look like? Any intuitions? So in the time signal, how will it look like? Right? Like, if I transform in Fourier, what should I look like? You saw that Daniel's transformation was kind of.
I mean, it's mostly going to be one mode.
So how will it look like in red? If you had to
A
picture,
spike one.
should look like a spike. If it was a pure frequency, which is extremely annoying to hear, if you have ever heard these MIDI frequencies, it's awful. That will look like one single spike because it's telling you I only have that. But this has, go ahead.
Really, it's going to be like all the modes that fit in it. So it's going to be like some equally, I don't think equally spaced, but a few spaced. It's going to be like the mode of like the single sine wave, and then the two that would fit in there, and then the like three that would fit in there.
So I think you're describing harmonics.
Mm-hmm.
And for any of you, this is a first harmonic of the signal. For any of you that know music theory, what is happening is that the note is D. This should be like 200 and something hertz. I actually don't remember. But on top of that, there's going to be other modes that are excited, and that is what is going to give the cuatro its flavor. That's what it gives my voice that flavor, even though I sing the same note. Sounds different, and that is all those other peaks. So we're going to see a bunch of peaks. Are you ready to give it a try? So at the count of 3. 1, 2, 3. Okay, let's see. The moment of truth. I'm going to save this. D note. But did I put caps? D note, I put caps. Look at that beautiful thing. Ain't it cool? And those are the modes that you're reconstructing. Let's look at how they look. So this is if you keep only 50, if you keep 500, 5,000, it's much easier to reproduce than the human voice. Just listen to them, at least the first two. You heard it? starts sounding like a video game, like a very old one. And I think this one is going to sound almost perfect. Not almost perfect, but better. Okie dokie. So this is in the GitHub repository. This is a way, this is the last two things that I say. This is a way also for you to gain intuition whenever we start talking about Dirac delta functions, Heaviside delta functions, and all of that nonsense, why the Fourier transform of them relate in the way that they do. If I have a single sine function with a given frequency, if you look at the coefficient in the Fourier space, what is going to tell you? Exactly what Alex was saying. It's a single frequency, don't use anything else, that's a delta function. And turns out if you transform a delta function, you actually get a sine function. And with the Heavisides, it's something similar, but we'll get that intuition later. So with that, I'm going to close with your playground for today. It's just me praying, please take a look at any of the other playground, just grab one and comment something on the GitHub repository or the forum. You could even comment, I heard the podcast and it's amazing. Now I understand imposter syndrome and I feel better about it. Any questions before we close?
Do you still want our email?
I will love it. So what I ask you, you should have my email. It's in here somewhere. Send me an email. Pablo, this is me. This is my email. Please add me to the list. And I will compile a list of you all so that we can, so that I can announce it. And thank you, friends. I'll let you know, Hannah, when everything is stopped in here. I'm going to start collecting things. Thank you all. See you for the last class of math. And we go for ice cream.